So, welcome to my course on calculus of one variables. Those who have taken my course on basic calculus, they have learned both one variables and two variables, but too much thing was compressed in too little time. So, I decided to make the things much more detailed, much more relaxed. Today, we are going to start speaking about numbers. You might think that why you need to speak about numbers. Numbers are so fundamental, we use it every day to buy our groceries, to pay for our tickets, to look at the cricket score, everything is done through numbers. So, human society thrives because of the existence of numbers. In fact, a very famous German mathematician, whose name is Leopold Kronecker, he once made a very famous statement. The statement is that God gave us the natural numbers, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then everything is man's handiwork. Once you have that, you can do everything. But do not ever think that numbers is something which you didn't really not bother about, it is so common. Of course, you know about these basic numbers. So, it is so obvious that I do not need to explain to you why and how of this. Now, the importance of the numbers is the following. These numbers introduce into our study what we call abstraction. So, what does abstraction mean? Abstraction means using a single symbol to represent different things. For example, if I talk about say 2 oranges and I say about 2 elephants, so this same 2 is representing that quantity 2, the same symbol. So, it does not matter whether it is orange or whether it is elephants. So, this is something we have to keep in mind, that it brings in the notion of abstraction. However, let us look at from a modern point of view. From a modern point of view, the mathematical language is the language of set theory. Set theory you must have learnt at school. These are some things which contains objects. Do not try to define sets as well defined collection of objects and all those things, because that will get into logical problems. So, you know what a set means. So, you always had some say number of one set is a set of your friends or set of your classmates, set of all say cars in India, or set of all potholes in the city roads. So, set theory, the theory of sets, was first introduced and studied by somebody called George Cantor. And in his language, the set of natural numbers is put into a set n, symbol as n. So, this set consists of all the natural numbers that we have. So, this is called the set of natural numbers. This is called the set of natural numbers. Now, if you observe very carefully, this 1, 2, 3, 4, 5, 6, 7, 8, this keeps on going, it does not end. And this is the first time you are possibly, you see in your very basic thing of life 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dot 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 dot, you are coming face to face with the infinite. Because this is, I think, your first example that you get, which that you are taught in mathematics, is an example of an infinite set, the set whose elements are infinite, not finite. So, this is not the kind of set that you have studied really in school, and George Cantor really bothered about sets of this kind. His teacher Leopold Kronecker, Leopold Kronecker supervised the thesis of George Cantor, but unfortunately his studies of having a headlong crash with the infinite was not really appreciated by his teacher. For his teacher, infinity was just a notional thing where you take limits and do all sorts of things which we will soon learn, but to him, to George Cantor, infinity was a real thing, and we will see something in the next classes also. So, this is the set of natural numbers. Some people try to define what is called a set of whole numbers by introducing 0 in the set of natural numbers. So, I will use these symbols of union, intersection, all those things, assuming that you know these basic facts of set theory from your school days. So, is this enough for us? The fact is that it is not enough for us. See, given an object here, we can define something called addition of these two numbers. So, if I have 2 apples in one box, 3 apples in another box, I can bring them together and make them 5 apples. But there is the issue of subtraction. So, if I have 3 apples in a box, can I take away 5 apples from there? If I ask a very stupid, possibly a question like that, then is there any answer to this? That gives us the idea of negative numbers. In fact, Blaise Pascal, one of the very big mathematicians of the 17th century, 17th I guess, 17th century, he made a statement that how can you think of taking away something from nothing. So, but negative numbers are real, your bank balances go in negative, many of us have negative bank balances. So, in that case negative numbers are real. So, this introduces us to the set of all integers. So, the set of all integers contains 0, contains 1 plus 1 plus 2 plus 3, which is nothing but 1, 2, 3, just to separate them from minus 1, minus 2, minus 3. This is also an infinite set. This Z, this symbol comes from the word Zahl. Zahl actually means number in German. I am not mistaken, possibly Richard Dedekind, a German professor, at first introduced this symbol. Now, at your school level, you are also taught about fractions. That if I have single cake and I have to divide them between 4 people, then I have to divide it into 4 parts, and everybody gets 1/4 of the whole, right, if I want to divide them equally. So, fractions are also a part of our daily life which we cannot ignore. When we use pure integers to denote fractions, we introduce something called a rational number. So, very loosely we can tell that we are talking about fraction, but fraction actually means something more bigger. It is not just what we are trying to say. So, here we are going to talk about rational numbers. So, we are essentially trying to talk about the fractions that we study at school. So, what are rational numbers? Rational numbers are any number, say R, which is expressed as the ratio of two integers p and q, where q is not equal to 0. Of course, you know very well that division with 0 is not permissible, and here p and q both are in the set of integers z. So, now we have got our natural numbers or negative numbers, we have got 0, we have got fractions. The question is, do we need anything more other than these rational numbers? See, this thing that there can be something other than rational numbers was first came from geometry, it did not come from basic algebraic manipulations. If you take a right angle triangle, and this is the most famous description of it, whose both sides are say 1 centimeter, then applying the Pythagoras theorem, the hypotenuse would have a length root 2 centimeter. And it was one of the Pythagoreans, you know, the great Pythagoras had a clan, a secret clan, who had access to knowledge about the world, and they wanted to keep it secret. They believed everything was natural numbers and fractions. They did not believe there was something else. So, when this came out, and one of his students called Hipparchus, who actually proved that root 2, this number root 2 cannot be expressed in the form p by q. So, we will show all these things in the third lecture, but we are just going to mention that this root 2 was shown by one of the Pythagoreans to be not rational, and the Pythagoreans were aghast. Hipparchus was thrown in the sea and killed because he made such a statement that there is something other than rational numbers. So, what we have obtained this far using the language of set theory is the following, that we have the natural number set, which when added with 0 makes the whole number set. Then when negative numbers come in, you have the integer set, and every integer can be written as that integer divided by 1. So, all the integers come in the set q. The set q is called the set of rational numbers, which I have not introduced earlier. So, there are certain numbers which are not expressible as p by q, for example, root 2. Root 2 is thus called an irrational number. In fact, we will show in the next lecture that irrational numbers are more in abundance than rational number. So, any number which is not rational, that is, that cannot be expressed in the form p by q, is called irrational. Okay. Now, is there anything beyond irrational? Of course, you can imagine that there cannot be anything beyond irrational. So, you have the most obvious things, there is fractions and standard numbers, negative, all that you can do with numbers. So, you would be perfectly happy just to have rational numbers, but unfortunately geometry, which is also a very real thing, gives us something very different story, because here you have taken sides whose lengths are rational numbers, 1 centimeter. So, irrational number is a reality with which mathematicians have to put up, and they play a pretty major role in mathematics. So, then if I denote, where C denotes the complement of a set, so the complement of the set of all rational numbers is a set of irrational numbers. This is what we have. And now, we introduce the super number set, which is called the set of real numbers. These are the numbers which we really need. Real in the sense that these numbers seem to exist actually in reality, in the sense that okay, we can actually find them even irrationals root 2. So, R, the set of real numbers, is nothing but the intersection union of Q with Q complement. Of course, you know Q intersection Q complement is empty, and there may not be a number which is both rational and irrational. So, hence the union of these two forms what is called the rational number set. Now, we will start talking about properties of rational numbers, and in that we will start first talking about the natural number set, its properties. That is quite important actually. You should have some knowledge about the set of natural numbers. So, we are now going to talk about the properties of natural numbers. So, we have started dealing with something called the infinite set. From the very beginning, we have started dealing with the infinite, and the infinite is very much of a reality in calculus. We can't really get out of that. So, these natural number sets are classified into two different sets called odd sets, set of odd numbers and even numbers, which you know from very basic school mathematics, which I just repeat for your convenience, which I need not have bother also with. Now, apart from these two classifications, there is an interesting class of numbers. One of the, see, there are 4 arithmetical operations that you carry on these numbers. One is addition, subtraction, multiplication tables of course have to do with natural numbers, and you also carry out division. So, when you carry out division, which is the inverse of multiplication, you come to some interesting classes of numbers. So, they are called the prime numbers, and they are very important in the understanding about if you want to understand about natural numbers. So, what are prime numbers? These are also taught at school level. Any number that is divisible by itself and 1 is called a prime number. So, prime numbers means divisible by itself and 1. So, you can say okay, I can start with 1 is divisible by itself and 1, but 1 is not taken to be a prime number. We will soon tell you why it is not taken to be a prime number. So, our prime number starts with 2, then 2 is the only even prime number, and then it goes to 3, 5, 7 and so on, so 11. An important fact about natural numbers is something called unique prime factorization, which I am writing on this side. It is a very important fact. It is called unique prime factorization. So, what does it tell me? It tells me that if you give me any number n, you can try out, I can always express it as a product of the powers of prime factors, right. Means a factor is a number which divides discrete numbers. Among the factors there are some numbers which are prime numbers, and you can always express it in this way. For example, so n can be written as, so if we take P1 to be a prime number, P1 to the power Q1, say PR to the power QR. You can form of, for example, 60. 60 is 15 into 4, 15 is 3 into 5 and 4 is 2 square, that is it. So, all the numbers are prime. So, and this representation is unique. Now, suppose I had considered 1 to be a prime number, then 60 could have this representation. Unique also means these powers are also unique. Every number has that. So, once you do take one as a prime number, this is what can happen. You do not have a unique prime factorization. That is the reason why 1 is not taken by convention to be a prime number. So, this is something important and has to be kept in mind. This is a very, very powerful result actually. This idea would be used to show that every natural number has a prime factor, would be used to show that there are infinite primes. So, that is a very key result about numbers which has to be understood. And one of the important properties about natural numbers is that it allows something called the method of induction. So, what is a method of induction? Method of induction is the following, that if you have a mathematical statement involving the symbol n, so you have to decide whether the given statement is true or false. So, the method of induction says first check if P1 is true, and then if Pn plus 1 is true, when Pn is true, then Pn holds for all n, holds for all natural numbers. This is a method of induction. For example, if you take this very simple statement, so my Pn is the following, this is what I want to check, is this true? So, obviously P1 is 1 here, and you can put n equal to 1 and see the left side is also 1. So, P1 of course satisfies this. So, now you assume that Pn is true. So, what is Pn plus 1? In this case the statement Pn plus 1 is of course 1 plus 2 plus 3 plus n plus 1. This simply tells me a simple fact that because I know that this is true, I can use this, that up to n it is true. So, this simply gives me n plus 2 into n plus 1 by 2, which is same as n plus 1 into n plus 1 plus 1 by 2, and hence this holds for n plus 1 also, showing that this result actually holds for all n. So, combining these two features of induction as well as the fact that you have a unique prime factorization, that hence we will now show that we have an infinity of primes. So, this result is a very ancient result which also is present in Euclid's Elements, that famous, one of the most famous books in mathematics of all times. Now, we will not do Euclid's proof, we will do a very modern proof taken from a book called the Proofs from the Book. Actually, the great mathematician Paul Erdos used to think that God, whom he called as the supreme fascist, that he has a book in which all the best and most elegant proofs of mathematical results are kept. So, we have to figure out that whether we can do better than the book or not. So, it does not mean, so mathematical research does not always consist of the fact that you have to do always something new. You can have look at old things from a very new angle and get newer insights. So, here is our first theorem. So, because we are doing mathematics, we have to come into the structure of the subject, and our first theorem is that primes are, there are an infinity of primes. To do this proof, we will take the help of something called Fermat's number or Fermat numbers. A Fermat number is a number, so we are doing a proof. So, Fermat number is a number of this form. For any n, the Fermat number is 2 to the power n plus 1. You can ask that who conjured up these strange things that you would prove like this. Of course, it need guess and test. It has come through many guessing and testing. The original proof of Euclid might look much more straightforward compared to this, but this is something interesting, and so I just want to show you this. That what happens that if you realize that this number is always an odd number, because 2 to the power n, any power of 2 is an even number. So, this is an odd number. Now, I will take 2 Fermat numbers and show that they are relatively prime. That is, their greatest common divisor or HCF, if you talk about a school language, is 1, right. So, there are no other prime numbers which are a common divisor to this. Okay. And every prime number is bigger than 1. So, there cannot be no prime number which is a common divisor to 2 different Fermat's number. So, that is why they are called relatively prime or co-prime. So, if I have a number, if there are two numbers, so given a prime number, if it is a divisor of say A, then it cannot be a divisor of B if A and B are co-prime. Now, you can understand as I keep on changing n, because the set of natural numbers is infinite, I have infinite number of Fermat's number. So, this Fermat's number is infinite numbers. You have infinite number of Fermat's numbers, while I will show that give me any pair of Fermat's number, they are co-prime. So, there cannot be a given common prime which is a factor to both of them. So, for each of the Fermat's number there should be different primes. So, if Fermat's number is infinite, so are the number of primes. That is the whole idea. Okay. In order to do this, we really use this very important recursive relation. We will show it by induction actually, and n of course is greater than or equal to 1. Now, assume that so f k, so here k is of course strictly less than n, because k is from 0 to n minus 1. So, let q be a divisor of f k and f n. So, you are talking about common divisors. Now, if it is so, if it divides all the f k's and f n, so it is a common divisor, right. So, here so for some k, q has a divisor, when a q is a divisor of f k and also of f n. So, what would happen here? I have a product of numbers. So, if I divide this side, it is completely divisible because q is dividing, but then this side should also be completely divisible, then the inequality makes sense, which means because f n is also divisible by q, which means 2 also has to be divisible by q, which means q, this would imply that q is equal to 1 or q is equal to 2, right. Now, q cannot be 2, because if q is 2, if q and q divides f k, then f k must be even. 2 only divides even number, 2 does not divide odd numbers. So, q cannot be 2, this is a conclusion, since f k is odd, which means what? Q is equal to 1. So, only common divisor possible between any fk and fn here is 1. So, for any pair you take k less than n, for any pair fk fn that you choose, or any fk1 k2 where u2, for any pair fk fn that you choose, does not matter now. You can do the same thing. If you choose any k less than n, you can do the same sort of induction, same sort of recursiveness, same structure with something lesser. So, whatever k you choose from here, the only positive common factor is 1. So, then which means we have proved that for any two pairs of Fermat numbers, they are relatively prime, and hence it shows, as we have discussed, that prime numbers are infinite. You see, this is a very beautiful and simple proof. And now by induction we can show that this is actually true. So, here instead of n minus 1, I have to add 1 here. So, I come to this simple fact k equal to 0 to n minus 1 . So, once you do this, I would request you, it is all given in the notes, I am not doing the proof, that put in Fn, what is the structure of Fn? You know this Fn is given as this one. So, use that and finally prove that this is nothing but f of n plus 1 minus 2, that is what you can prove. So, now we are coming more into the rational number things. How do we represent rational numbers? There is an interesting way of representing rational numbers called decimal representation. So, decimal representation means I am looking at multiples of 10, right. So, or division through multiples of tens. So, that when we give representation through multiples of 10, that gives rise to decimal representation of numbers. Now, so any rational number or any fraction, if you want to be just more loose, fraction is actually a more broader term than rational number, because I will tell you later why once we introduce functions. You see, if you take a rational number, say p by q, then if you multiply them by any non-zero number r, then p by q is same as rp by rq. So, this is something you have to understand. Now, decimal representation means that you can represent, there is something called a decimal point, and which is the point, and sorry, there is something called decimal point, and on the right hand side of the decimal point there will be some chain of numbers. So, decimal representation is important because it shows if the number is between 0 and 1, the left hand side of the decimal point where you have the whole numbers actually, that part would be 0. So, you have already done some decimal points while trying to learn division in school, but we will talk about something so in more detail. So, rational numbers are of two types. So, if you take the set Q, they have two types, one which is represented by terminating decimals, another is representing by infinite decimal, that is they do not terminate. The decimal points, as you keep on dividing a bigger number, a smaller number by a bigger number, on the right hand side you will keep on getting, your division will continue, your division will continue. So, these decimal things arise through the division process, right. For example, if you say half is 0.5, but luckily the number 1 can be expressed as a non-terminating decimal. You might be wondering how come this would be equal to this. Actually, it means as you keep on increasing the 9, the distance between 1 and that number would go to 0. here also is hidden the stamp of the infinite, which will come in more detail later on. For example, 1/3 would be 0.33333. So this is a terminating decimal. This is an example of a terminating decimal. These are examples of non-terminating decimals. Okay. Now, take this for example, this nice explanation given by Niven, that when does of course, you would like to have a terminating decimal other than non-terminating decimal. Terminating decimal looks much more nicer. So, you ask the question, when would P by Q give me a terminating decimal? That is the question. When will it give me a terminating decimal? So, consider this example. So, this is nothing but 8625 as you have learnt in school divided by 10,000. Those are 4 digits. So, after 1 you put 4 zeros, and this is same as 69 by 80. You observe that the greatest common divisor between 8625 and 10,000 is 125. The greatest common divisor, or HCF, whatever you want to call, GCD, between 8625 and 10 to the power 4 is 125. So, if we divide, we have basically divided both the sides by the greatest common divisor. Now, if you look at 80, so this is a terminating decimal actually. Now, we have brought it into a rational number form. Now, look at this 80 and look at its prime factorization. Its prime factorization gives me what is this? It is, I can write it as 20 into 4. So, 5 into 4 into 4. So, 5 into 2 square into 2 square. So, it is 5 into 2 to the power 4, 60 into 5, that is it. So, this is actually its prime factorization. So, what is happening, that when you have a terminating decimal, it looks like as if the lower, when you put the thing in the see what is happening, that the lower thing, because you are ultimately dividing by the grade GCD to get the P by Q in the lowest form, you cannot do any more your cross cuttings that you have learnt in school, any more divisions. So, what in this case what happens, what is 80? What is this? This is nothing but a factor of, or rather this number is a multiple of this number, because you have divided by the GCD. So, GCD into 80 is this, so it is a multiple of this number. So, you have observed that because 10 is equal to 2 into 5, the only prime factors of this number is 2 into 5, and so only prime factor of this number will also be 2 and 5. So, a decimal can be a terminating decimal if you have a rational number, and if Q's only prime factors are 2 and 5, you will always get a terminating decimal, and that is the correct fact, and this can be actually proved, which we will not statement, which you can look into it later on. Now, but among these, so this is about terminating decimal. What about non-terminating decimals? So, we will discuss about non-terminating decimals and finish. Do they have some pattern? Non-terminating decimals have some interesting pattern. So, if you look at this number, say 5 by 11. So, I am giving these expressions from a very beautiful small book called Numbers, Rational and Irrational by Ivan Niven. Very well written, very beautifully explained book. So, if you look, you see 4 5 4 5 4 5 gets repeated. So, what is happening? So, for example, you take 3097 by 9900, you have 0.31282828. So, initially the two things are not repeated, then again it is repeated. So, the shorthand of writing this is 0.45 bar and the shorthand of writing this is 0.3128 bar, the shorthand. So, it means that these things are repeated periodically. So, every non-terminating decimal has some periodic structure built into it, that one particular patterns after some time one particular pattern will keep repeating itself. So, why this happens? This just because of division. It's simple division. For example, you take the number 2 by 7. Let us see what sort of a 7 is a prime number. So, it cannot have 2 and 5 as its prime factors, right. The only factors are 7 and 1. So, this means it cannot be a it cannot be a terminating decimal, it must be a non-terminating decimal. So, let us see if I divide 2 by 7 what would happen. So, here is a 7, 2 can be written as 2.000000. So, first is of course 0, 0, then you put a point and you have 20. So, you 2, 7 to the 14, 6, you take 60 and I am just writing it down. I am writing down the answer which you can verify because this is very simple to do. I need not do this thing repeatedly. You can do this So, what is happening? You have started with these divisions and finally, you come back to 2, 20. So, again you start over from this 2 and once you start from this 20, see 7, if it is 7, what could be the remainders? Remainder has to be less than 7, it has to be 6, 5, 4, 3, 2, 1. So, once you have record, if any one of the things have record here, then you go back, the division process again goes back. So, this number again gets repeated. So, 2 by 7 is nothing but 0.285714. So, it is not that the very first number would always get repeated. Maybe the second or third number remainder suddenly it will get repeated. So, from there the pattern would start repeating again. So, you can check this out by dividing, for example, I will give you an exercise just to check, as you can take as a homework, and it will be quite a good amount of fun to understand what actually happens. You will really understand that 2 need not start repeating here. So, some other remainder can start repeating and so the factor would just go from that point. In this case, P by Q, this can be represented, you just can do the division and just see. So, it is the second remainder which starts repeating here and this is what happens. The very interesting fact is that is given in the notes, I will not do the proof here because of time, is that if you give me any repeated decimal, I can always represent it by a rational number. So, any decimal which is a periodic representation like this can always be represented as a decimal number. This will be in the notes, so you can see it from the web. So, in the notes we have also spoken about real numbers and what are the rules of handling combining real numbers, because those rules are rules through which you do addition, subtraction, multiplication. For example, you will see a rule called distribution of multiplication over addition. This is exactly the way when you multiply a 2-digit number with a 2-digit number or 3-digit number with a 2-digit number, that is exactly what is happening. That rule is actually followed. For example, when you learn at school, obviously you do not know that there is a very basic rule that has been followed. So, we have now some broad idea about numbers, how to handle them, and what are the properties. You see that prime factorization is such a crucial idea, and that is why it was introduced. And with this I stop for today, and tomorrow we are going into the world of countability, uncountability, the finite and the infinite. Thank you very much.